All right, so I'm gonna go ahead and run all. Once it's done. All right, so this beginning part is just importing all of the things we're going to be needing to do this. So plots, and then this Newton, which is a root finding method that uses linear approximation and allow us to kind of get our value that we're looking for with the temperature of the air feed to converge. Next, I went through, and these are just a bunch of knowns that were given in the problem statement. And literature values as well. This is an equation to solve for Kc using the equation that I solved for from part 1. It was the very last equation that I did. And then this is an Antoine equation to help determine the vapor pressure. That's what this PV stands for. So it's defining the vapor pressure at a specific temperature. And it's in pascals. That's what this conversion factor is for. To just make sure that that pressure is in pascals instead of anything else, any other unit. And these are just more knowns. This Z end is the length of the cooling tower. I do have it initialized up here as length, but we picked Z end because we're calling it DZ, or change in position. We have our exit temperature, our exit mole fraction for the air, the feed temperature of the water, and this is, as stated in the problem statement, we wanted our initial temperature of the air feed guess to be the same as the exit temperature, which we know is not correct, but that was our just initial guess. We are our Z, so our change in position, we're having it go from 0 to Z, and we're having 50 points. This section is to start solving our differential equations. So this is to get our feed temperature to converge towards what the actual temperature of the feed should be. This is the formula that we solved for. Now we are defining our change in position with respect to these three elements, our mole fraction, the temperature of the water, and the temperature of the air. These are the calculations needed for average molecular weight, because we needed the flow rate of the air and the mass molecular weight of the air, and so we needed to have those equations initialized beforehand. This again is another important part of the equation, which is the concentration of water at the interface, which is just equal to the pressure at the temperature of the water. That's what this parentheses TW means, divided by the gas constant times the temperature of the water. So this is at the temperature of the water, and then this is times the temperature of the water. Next, we solve for the molar flux of the water in mole per meter squared seconds, using that concentration of the water at the interface. And then this is the concentration of the water at the bulk, but instead of doing a formula for it, we know that the mole fraction times the pressure gives us that partial pressure anyways. So we just went ahead and used that instead of making a new variable. These are just more equations from part 1. We have our water differential equation and our air differential equation. Then we return those three values and solve. Use our Newton linear approximation to get our feed temperature to converge from our guess. And then we have these three scatter plots that we make, these three graphs of our water temperature, our air temperature as it changes through position, and the water partial pressure as it changes through the cooling tower.